Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase medium length transmission line. By solving this problem, we shall learn how to determine voltage regulation of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. A balanced three-phase load of 50 megawatts is supplied at 132 kilovolts, 50 Hz and zero point 0.8 power factor lagging by means of a transmission line. The series impedance of a single conductor is 20 plus J times 50 ohm and the total phase to neutral admittance is 300 micromho. Shunt linkage may be neglected. Using nominal T approximation, we have to calculate the voltage at the sending end of the line. If the load is removed and the sending end voltage remains constant, we have to calculate the percentage rise in voltage at the receiving end. Let us now write down the given data. Power delivered to the load PL equals to 50 megawatts, that is equal to 50 into 10 to the power 6 watts. Line to line receiving end voltage VR line equals to 132 kilovolts, that is equal to 132 into 10 to the power 3 volts. For star connected system, receiving end voltage per phase VR equals to VR line divided by root 3, that is equal to 132 into 10 to the power 3 divided by root 3, that gives us 76,210 volts. Given load power factor cos phi L equals to 0.8 lagging. Let us now calculate power factor angle. Phi L equals to cos inverse 0.8, that is equal to 36.8699 degree. Expression for power delivered to the load PL equals to root 3 times VR line into IL cos phi L. Therefore, load current IL equals to PL divided by root 3 times VR line into cos phi L. Using values we get 50 into 10 to the power 6 divided by root 3 into 132 into 10 to the power 3 into 0.8. That gives us 273.3666 ampere. Load current may be written in polar form as IL equals to IL at an angle minus phi L, that is equal to 273.3666 ampere at an angle minus 36.8699 degree. Taking receiving end voltage per phase as reference, we can write VR equals to 76,210 volts at an angle 0 degree. We have computed load current IL equals to 273.3666 ampere at an angle minus 36.8699 degree. This may be written in Cartesian form as 218.7 minus J times 164 ampere. Given series impedance per phase of the transmission line Z equals to R plus J times XL, that is equal to 20 plus J times 50 ohm. Now we shall calculate per phase impedance of half of the transmission line. ZH equals to half of Z, that is equal to 10 plus J times 25 ohm. This may be written in polar form as 26.926 ohm at an angle 68.2 degree. Given shunt admittance per phase Y equals to J times Vc equals to 0 plus J times 300 micromho. This may be written in polar form as 3 into 10 to the power minus 4 mho at an angle 90 degree. Let us now calculate capacitor voltage per phase. Vc equals to VR plus IL into ZH. Using values we get 76,210 at an angle 0 degree plus 273.3666 at an angle minus 36.8699 degree into 26.926 at an angle 68.2 degree. That gives us 82,497.379 plus J times 3,827.3118 volt. This may be written in polar form as 82,586 volts at an angle 2.6562 degree. Now we shall compute capacitor charging current. IC equals to Vc into Y. Using values we get 82,586 at an angle 2.6562 degree into 3 into 10 to the power minus 4 at an angle 90 degree. That gives us 24.7758 ampere at an angle 92.6562 degree. We have computed capacitor voltage per phase Vc equals to 82,497.379 plus J times 3,827.3118 volt and capacitor charging current IC equals to 24.7758 ampere at an angle 92.6562 degree. This may be written in Cartesian form as minus 1.1482 plus J times 24.7492 ampere. Now we shall calculate sending end current. Is equals to Ic plus IL. Using values we get 217.5518 minus J times 139.2508 ampere. This may be written in polar form as 258.3 ampere at an angle minus 32.6225 degree. Now we shall compute sending end voltage per phase. Vs equals to Vc plus Is into ZH. Using values we get 82,497.379 plus J times 3,827.3118 plus 258.3 at an angle minus 32.6225 degree into 26.926 at an angle 68.2 degree. That gives us 88,154.084 plus J times 7,873.756 volt. This may be written in polar form as 88,505 volts at an angle 5.1 degree. For star-connected system, line-to-line sending end voltage Vs line equals to root 3 times Vs. That is equal to root 3 into 88,505, which is approximately equal to 15.33 into 10 to the power 3 volts or 15.33 kilovolt. Now we shall remove the load from the receiving end and calculate capacitor charging current on no load. ICO equals to Vs divided by ZH minus J times Xc. We have computed sending end voltage per phase Vs equals to 88,505 volts at an angle 5.1 degree. Per phase, impedance of half of the transmission line ZH equals to 10 plus J times 25 ohm. Given capacitive susceptance per phase, Pc equals to 3 into 10 to the power minus 4 mho. Let us now calculate capacitive reactance per phase. Xc equals to 1 upon Bc, that is equal to 1 upon 3 into 10 to the power minus 4. That gives us 3333.3333 ohm. Now we shall calculate ZH minus J times Xc. Using values we get 10 minus J times 3300 8.3333 ohm. This may be written in polar form as 3300 8.3484 ohm at an angle minus 89.8268 degree. Using values we get ICO equals to 88,505 at an angle 5.1 degree divided by 3300 8.3484 at an angle minus 89.8268 degree. That gives us 26.752 ampere at an angle 94.9268 degree. We have obtained capacitive reactance per phase Xc equals to 3300 33.3333 ohm. No load capacitor charging current ICO equals to 26.752 ampere at an angle 94.9268 degree. Now we shall calculate receiving end voltage per phase on no load. VRO equals to ICO into minus of J times Xc. Using values we get 26.752 at an angle 94.9268 degree into 3300 33.3333 at an angle minus 90 degree. That gives us 89,173.332 volt at an angle 4.9268 degree. Now we shall calculate voltage regulation, that is equal to VRO minus VR divided by VR. We have computed receiving end voltage per phase on load VR equals to 76,210 volts. Therefore, voltage regulation equals to 89,173.332 minus 76,210 divided by 76,210. That gives us 0.17 per unit or 17%. So today we have solved one numerical problem on three-phase medium length transmission line. By solving this problem, we have learned how to determine percentage voltage regulation of a three-phase medium length transmission line using its nominal T equivalent circuit when load details and values of transmission line parameters are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.